All right. Good afternoon, everyone. Good morning, good evening, depending on where you join today's session. I'm excited to have all of you here today. My name is David. I'm co-founder here of SimScale, CFD engineer by training. And before we dive into this, a couple of technical notes in the beginning. We're using GoToWebinar to stream the session, and so you do have at any point in time during the webinar the chance to ask questions. I'd encourage you to do so. So there's a little window where you can type them in, and I'll try to cover as many as possible of them later on, and after by the end of the session. We do have a pretty packed schedule today. I'll try to keep it as crisp as possible for you, that this is not going to be a death by slides today, and that we have some time to dig into the questions. So please make use of this feature. Afterwards, a recording will be sent around, so if you want to watch a specific section of the webinar again, you will have the chance to do so. Everybody will receive automatically the recording. All right, that being said, without further ado, what we'll talk about is pedestrian wind comfort today, specifically for architects, civil engineers that care about pedestrian wind comfort, also pedestrian wind danger, right, or risk assessment of master plans. And to manage some expectations, what we will not talk about today is the details of specific pedestrian comfort criteria or the details of specific codes, right? There's so many of them, so many different codes that are being used depending on where you're located, depending on the country, and that's not what the session will be about. What we'll talk about today is first and foremost why we see so many people using SimScale for these types of analysis. So why is SimScale a good tool for that? The second piece is what is it in SimScale, right, that you can do? What types of analysis are in there? What types of capabilities do we offer? And then last but not least, it'll actually be a small hands-on session here as well, right? So I'm going to walk you through a small live demo of one of the scenarios we're going to look at today that you not necessarily, can run a simulation yourself immediately afterwards, but at least that you get a good feeling for how it would be to use SimScale. The audience today is pretty mixed between users of SimScale already, right, and customers that are already actively using SimScale. For you, there might be also a few new aspects in the session today because we just recently released a new lattice Boltzmann solver, and we're going to see that piece of technology in action today for this for these applications. And then there's a lot of people that have not been using SimScale today. So I hope until today. So I hope for all of you there's a good mix that and it's a valuable session for you. All right. Few words for an introduction. I guess the fact that you signed up for this webinar, you have you're involved in pedestrian wind comfort, urban master planning, urban development, something around that, right? And this is the reason why we're here today, right? We want to make sure that the master plan layout, the buildings we're designing, the way we develop urban areas, make sure that for different types of activities, we do have pedestrians feeling comfortable. At times, it's even about risk, right? If you're looking at the wind on terraces or on high-rise buildings, you want to make sure that nobody gets blown away. But most of our customers are dealing with pedestrian comfort analysis, so where you want to make sure that for, recreational use, right here on the right, we can see a more scientific way of structuring different comfort criteria. And for different types of criteria, you want to make sure that your people, the pedestrians around your buildings, feel comfortable. And the way this is typically done, or the way a civil engineer or an architect can assess that is based on local weather data, right? That you get, there's so many databases, so many online resources that gives you the local weather data, the local microclimate, and that together with the master plan layout, so with the design you're putting together, alongside 3D wind effects, really how air is moving through small passages between buildings, through different geometrical shapes, gives you ultimately a map of how comfortable or uncomfortable pedestrians feel around the urban area you're designing. And the reason why we're here today, right, or the reason why so many people are using SimScale or CFD in general is that the little arrow here on the right, there's three methods to do that, right? So I'm really talking about, I think there's a highlighter thing here, right? So this here, right? So how do you get the information, how you design alongside the local weather data, actually what type of or what kind of pedestrian comfort map does it produce? And there's fundamentally three methods at your disposal. One is a full-scale test, right, which is rarely being used. And then there's wind tunnel testing that is more regularly used, a more traditional method. And then over the last, I guess, decade or so, CFD has become in that realm, right, more and more the tool of choice, because it allows you to do these types of analysis, that predicting how your layout will influence pedestrian wind comfort much faster, much easier. And the industry, the CFD industry in general, the CFD software vendors have become pretty good at it, right? So there's meanwhile a whole bunch of tools that allows you to do that. Let's erase that again and go back. Okay. And before we actually get to work with some case studies and with some actual simulation work, let's quickly make a step back and put the types of simulations we're going to run in a second in some further context, right? This is a little chart I like to use to visualize that. At the bottom, you can see the building design timeline, right? Roughly, or in that case, a master plan layouting process, and roughly put into different stages, from concept down to finalized design, and you're entering the bidding phase. And on the y-axis, we can see project cost, as in, a building, urban area, urban environment, call it whatever you want, how the costs arise for the development of a specific area or building. And there's really two different types of graphs I want to put in here. One is cost realization. The cost of this entire project, right? Keep in mind, this is the design process, right? It's not yet the construction process. So for the overall project, only a small fraction of costs of the overall project goes into the initial design, right? In these different stages, right? Architects, engineering work, MEP, you name it, right? All these people want to be paid. And interestingly enough, how the costs for a specific project are defined, this looks very different, right? Obviously, after bidding, there can also be cost changes, or there can cost occur. But the biggest piece of how much your project will cost, how much the development of an urban area will cost, and what kind of downstream costs will occur, are being defined in a very early phase, right? Because this is where the big decisions being made, the fundamental decisions, how a specific design will look like. And it's this, I guess, very asymmetric behavior between cost realization and cost definition that makes simulation, CFD, such a powerful tool. And today we're going to look at two different types of scenarios, two different types of simulations we're going to run today. One will be in a very, very early design, really in a conceptual design phase of a building, or an urban area for that matter. And another one will be at a very detailed stage of the design process. So we're about to finalize the plans and enter the bidding phase. The reason why we're going to look at two different projects today is that the type of CFD, the type of simulation you want to run in these stages are very different, and that's something we're going to look at later. Yes, and these are here the first real colorful pictures, but these are the simulations we're going to run today. So why two different projects, right? Why am I saying that there's two very different types of simulations you want to run? Let's dig here a little deeper. The first one will be a scenario where the project just got kicked off, right? So there's an urban area, you have some environment, some building environment, some surroundings, some terrain, and you have development projects where a couple of buildings in that urban context are to be designed, right? Very early in the process. The types of simulations you need at that point are, you want to be fast, right? It's rough sketches. It's you might use tools such as Rhino or SketchUp, very rough layouts. There's not a lot of detail to the facade design yet, etc. It's really sort of the master plan, right? And what we see customers appreciating here is that you are able with SimScale to run very fast, quick iterations that don't take you a lot of setup time and also not a lot of compute time. We're going to see that in a second. You oftentimes don't do, all wind directions and from all different angles and with different velocities. You typically look at the primary four ones, or sometimes even just one direction, right? Depending on the location. You're also not looking at detailed atmospheric boundary layers. For the CFD engineers in the audience, you're not even looking at super detailed velocity inlet conditions, because you want to iterate fast, right? It's not about gaining super high accuracy, because what you want to do is you want to inform your design process. You want to make informed design decisions as you go along and leverage the fact that design changes at this stage are very, very cheap, right? Now iterating is cheap. Making a big design change after you've detailed out a design, this is costly. And so you want to have a fast iterative way of using CFD. The other scenario, very different. Towards the later stage of the design process, depending on where you are, depending on what regulatory compliance you need to comply with, you want to run a very detailed validation, right? So this is typically different simulation projects that we're seeing. So it's oftentimes just one very detailed study. You're looking at the entire realm of wind direction, so you want to make sure that you're capturing the local climate in very detail. You're investing much more compute power, so you want to run more finer resolution, because ultimately you want to comply with regulatory codes, right? With some standards, and you want to prove that with simulation. And this is really something that is very different from country to country. Sometimes there's even standards, such as in the Netherlands, where there's really already CFD encouraged, or at least enabled by the building standards or by the codes that are being used there. Sometimes it's just something the engineering office at that point wants to do. No matter what exact scenario, this is a very different type of analysis, right, that you're running. And I guess this chart shows nicely that on the left, decent accuracy, we want to be fast and iterative. On the right, high accuracy, it's okay if that simulation project takes longer. And we're going to look at both today quickly. Before we do that, right, all of this was rather generic about the use of CFD, the use of simulation in this context. Now the question is, what's special about SimScale? And that might be, sorry for the people that know already SimScale, it might be a quick repetition for our customers, but for the ones that are not yet familiar with it, the traditional software tools in the CAE realm, in the CFD realm, are oftentimes require a lot of hardware, right? Because you're forced to run to maintain hardware locally, so you have some sort of high-performance computing system on site. It comes down to a lot of software and hardware costs that you invest upfront before you can run the first simulations. And last but not least, because it's such a huge investment, this is typically done for a dedicated engineer, an analysis engineer that's using it on a daily basis. And this is where SimScale enters, right? This is why we built SimScale, to remove these traditional barriers of simulation tools. First and foremost, there's no hardware need, right? You're going to see all the simulations that I'm going to show you later in that session being carried out in a web browser. You start with a very low financial commitment upfront, and then you can scale as you need SimScale to scale, right? So you ultimately end up paying for what you use and need, not for what you put at some point in your server room. And then last but not least, because it's cloud-based, because it's everything runs in a web browser, there's completely new ways of how you can collaborate with each other and with our support team, right, with our support staff. So you can share simulation projects with a click of a button with support engineers here at SimScale. We use a lot of data science to automate the simulation workflow, to remove all of these know-how barriers that exist in traditional simulation tools. But again, don't take my word for it. We're going to see it later in action. That is the reason why we've seen a lot of companies adopt SimScale as a simulation tool. at this point, also an important thing to note, the architecture, engineering, and construction industry is really, one of our strongest verticals. So we see a lot of a lot of growth there in our customer base. But it's just one of them, right? We serve a lot of industries because these traditional barriers of simulation tools that I talked about they are around not just in the AEC realm, but in really any type of vertical where simulation is being used. But in the architecture space, we see a lot of success. And here's a couple of applications that you can do with SimScale. So we see at the top left, we see a few internal CFD applications. So this is a thermal comfort application of a theater. We can see here a passive ventilation of a shopping mall in the UK. On the right, a more special applications. This is a clean room for a microscope that a customer analyzed. Does ducting work, contaminant control, you name it. And what we're here for today is here in the lower right? Pedestrian wind comfort analysis, so a flow simulation or a wind simulation through an entire city district. And this is where we'll drill down today in further detail. But I guess the important takeaway here is that we see a lot of customers appreciating the fact that SimScale is not just a tool for one application they have, but which brings a realm of different applications you can solve on SimScale in the AEC sector. Now, this is a quick note on what you will see next is using a new technology which is recently added to SimScale, which is called Pacefish. It's a GPU-based lattice Boltzmann solver. And you can see on the left a little animation, right? This is actually very close to what we'll do today. So it can compute external aerodynamics applications with a trailing a so really incredibly fast, transient analysis incredibly fast. You're going to see it later. That would in turnaround times that are unseen with a final volume method or with another CFD method. It deals with geometric complexity in a very graceful manner, meaning that you can drag and drop. You're going to see that later as well. You can drag very unprepared CAD models into it, and it deals with it easily without a lot of preparation time. And then last but not least, accuracy. It's we have a lot of validation projects for it, and the beauty of it is that this exact same method that is very fast and that is robust allows you also to compute aerodynamic effects very, very accurately, right? That is important for the second scenario that we talked about. And I want to tie, at this point, this slide back to the two scenarios we talked about. A couple of slides ago, we said, okay, in a scenario one, in an early design phase of a building, you want to be fast, and you don't want to do a lot of preparation time, manual time. And so here we'll see the two lower, like the second and the third property, or I guess USP of Pacefish panning out. And because it'll allow us to just bringing in a CAD model, don't prepare it a lot, run the analysis, and you'll get faster turnaround times. And in the second scenario, we're going to see it being very accurate, right? So you can, using the exact same technology, using the exact same workflow, just by increasing the resolution with which you want to compute the wind through the city, you can compute highly accurate flows as well. And we're going to see that. All right, this was now a lot of slides, and I'm slightly running behind schedule because I really want to do some live demoing here. But let's dive into it. This is the first scenario, and with which we will spend most of the time in this webinar. We're going to the scenario 2, so the more detailed analysis. I'll keep that rather short. This is an example of a typical project we would see at SimScale, our customers simulating on SimScale. This is a typical master plan layout. You have some urban environment. You have a specific urban context, some buildings that are around that you cannot change, right? And then you can see the colored buildings that is part of a development project your AEC firm, your civil engineering office is tasked with in a project. And now, looking at this, one thing we don't see here in this setting is terrain data, right? It would also, we see a lot of customers also bringing in terrain data. So if you have some, hills or some, vegetation, that's also something that's doable. In this case, it's a flat terrain, so we didn't bring in the terrain as a CAD model. And in this specific project, it's very early, right? And so I'm making, you can see the buildings are really, roughly shaped, and I'm just interested in how does this influence my pedestrian wind comfort? Specifically, it's in an area, you can see it on the left, right, where there is a significant percentage over the year. We have the gust speed of 50 kilometers per hour from that direction, right, and coming from the left. And what we're interested in is specifically analyzing our layout for that particular velocity and wind direction. And you can see already right now here, right, in a detailed pedestrian wind comfort analysis, we would look at all wind directions and would weigh them according how often they tend to be throughout the year, right? Because this is an early design project and I just want to do some sanity checks first, I'm just going to look at one wind direction. The challenge at hand is, this is the top view, right? The challenge at hand is, let's zoom in here a little bit. You can see that we have some bigger areas around the buildings that we're developing, right? And the particular concern in this scenario is that these red areas are not roads. This is meant for recreational use, right? So some park where some vegetation is supposed to be put in, and where there's, think of a university campus, or we see at times also a train station, something like that, where you have some recreational elements. So we will expect pedestrians in this area, to sit, to relax, and hence the allowed wind speeds here before people feel uncomfortable are very low. So what we want to look at is, what is our wind doing in these areas? And now, finally, we're going to jump over to doing some actual simulation work. For the ones that are not yet SimScale users, you should see my entire screen, right? You can see this is a browser application. So we're running, this is a Google Chrome browser. SimScale provides an end-to-end workflow for CFD, completely cloud-based, meaning there's zero software install, there's no local hardware you need, it's just your web browser. And you can see here, differently colored, but this is the master plan we just looked at, right? And before we quickly simulate this, I want to point out the fact that this geometry is not well prepared for simulation, right? And so, there's all sorts of, nasty stuff, super thin sliver faces over here. Look at this, right? I have a model that I'm on a scale of, a kilometer by a kilometer, or, I think, roughly. And I'm having faces in here that are super small, right? I'm having a lot of nasty detail, overlaps. Can you see this, right? This is sort of overlapping faces, etc. Also over here, right? This is not even a solid, so we can see this is a shell, and it's not watertight, and etc. So it's a rather nasty model, and the reason why this is such a great example for the scenario one we talked about is that I don't want to spend my time now or invest a day of engineering work to clean up that model to run a CFD analysis, right? Instead, what I want to do is I want to just bring that from Revit or from, you name it, AutoCAD or Rhino, and just run a quick analysis with it and then inform my design process. And so that's what was done here, right? I think originally this came from Rhino, as far as I know. Imported into SimScale. SimScale runs on a Parasolid kernel, so inside SimScale, that's going to be a Parasolid model. Okay, and so you can see nothing prepared in this project, so we'll get into it right away. So we'll create a new simulation based from that, and we're going to choose the lattice Boltzmann solver we talked about. You can see there's all sorts of analysis you could run with SimScale, and then it's a rather straightforward process. The first thing we want to do is we want to set up the virtual wind tunnel, right? You can see this box, which is, in this case, very, very big. We're saying that's going to be a rough analysis, so we'll make this very, very small, just to save computing time. Probably too small, right, for that matter. Let me quickly define that. 0 there. 500 meters in that direction, 500 meters in that direction, and then let's say 200. Truth be told, this is, for the CFD engineers among us, right, there's typically this, there's rules, right, 2 or 3 model sizes in upstream wind direction, 5 to 8 model sizes in downstream wind direction. And so for more detailed validation studies, the scenario 2, I would want to make this much bigger, right? For our rough first quick analysis, this will do the job, and I'll just leave it like this. A second thing we'll define is I want to define a region of interest, we call it. And this means that later on, I want to save time in post-processing by basically just saying, I want to see where I'm specifically interested in the area where my pedestrians are, right? And so you can see that I defined a box on from 1 to 3 meters height. And this will allow me to much faster interrogate the results afterwards. I wouldn't need to do that. It's just something that'll do the job. That'll make my job later in analyzing these results much faster. The rest is actually not very interesting. Velocity, right? So we are seeing in positive x direction is our speed. So coming from the left, right? And so we're saying 20 meters per second. This is I think 54 kilometers per hour. And that's sort of the gust speed we wanna simulate. And then we're almost there, right? We want to run it for 100 seconds. So almost 2 minutes transient flow. And then we want to export our transient results exactly on this layer, right? So I'm interested in seeing the velocity on 2 meters height. I'm also interested in the average values by the end and in the snapshot values by the end as well. I'm going to explain to you in a second what this is about. And let's kick this off to make sure we have some results before the end of the session. Okay, if I haven't forgot anything, what we've done now is that we've defined a virtual wind tunnel analysis, right, in a very coarse way, right? We didn't specify an atmospheric boundary layer. We didn't specify a turbulence profile from the ground to the top, etc. All the things you could do once you're getting into a more, fine granular, into a more detailed stage of your design process. In our case, we've really done a very, very coarse, quick setup. And within, I don't know how much time was that now, 3 minutes or 2 minutes, we have a first simulation running. Now, while we wait for this simulation to finish, one thing I pointed out is that the exact same solver can be used for a more detailed analysis, right? And this is tuned via these settings, right, via the resolution or mesh settings. And in this case, we left the very coarse resolution, and we didn't tune anything here, right? What you want to do as you go more detailed into the design, as your design matures, what you're interested in is driving the resolution to get higher accuracy, right? And this is where you do it. So there's no huge mesh generation approach, or I don't know, CAD cleanup, yada yada yada, or for that matter, even structured meshing, structured gridding. None of this is part of the workflow. What you do is you can drive refinements, right? You could say, okay, I want to specify a specific resolution on the building surfaces. So I could, let's actually do that. We'll quickly do that. So I'm selecting all of my buildings here, and I'm saying, okay, I want to, resolve a feature on, down to 0.5 meter. No directional cells, and I could kick this off as well, right? And so now I'm driving the resolution up of my model, so I will invest more computing time, but this was literally 30 seconds work, right, to gain a more higher resolution for this. And let's kick this off as well. Let's try this as well. And now again, showcasing that SimScale can run simultaneously multiple simulations in parallel, right? Let's quickly hop back. And this now, the run one will be underway, right? We're going to see later when we look a little bit at how the results look like, how they feel, and how the analysis is being done. We're going to see how the post-processing, pre-processing, everything stays the same, and you're just tuning up the resolution to get a higher accuracy. Okay, while we wait for the run 2 won't finish in in this webinar's time, right? So this will take longer. But the run one, I expect, to finish within 5 minutes or 7 minutes. So the entire turnaround time on such a quick analysis is really literally like 15 minutes, maybe 20, right? And the manual time wouldn't go up as you increase fidelity of your simulation, but the compute time would, right? But we'll get a feeling for that in a second. Let's not just sit here and watch this, but rather, jump back and quickly continue. What we'll see, and just also to point out, right? The now the preparation steps for my simulation run are already done, right? It does a little of pre-processing, analyzing the geometry, etc. So that's why it was unqueued. And now you can see here in the run window that now the simulation is actually running, right? So we can see that that it's now progressing. So we're at 30%. So, and we could even already, once the first results have been streamed back from the compute instance, from the GPU instance, there you go, right? Transient solution fields just popped up, right? As soon as the first result fields are available, you can actually, visualize them as well. I want to wait until everything is done, but just to give you a feeling for how fast this is, right? So literally within 4 to 5 minutes, we're going to have arguably a course, but a first analysis of what my wind within this urban environment actually does. Okay, let's give this 2 more minutes and then we'll look at it. What we'll see, right, is something similar to this. So this is now a zoom in into the, okay, I forgot the scale here. This is 15 meters per second, right? 15 meters per second is red. And what we can see is that sort of a Venturi effect, definitely at the lower portion here, a Venturi effect happening. So within the channel between the 2 buildings we're developing, we can see that we have significant speed up, significant, almost a Venturi effect, so an acceleration of the velocity compared to the buildings around. And on the top, we can see that on this other place, while not as bad, we can see that we have some, some flow passage or some vortices going through here. So something also, that's not ideal. Let's quickly hop back. 70%, 80%. So we'll be there in a second. And let's quickly hop over. So at 86%, but I don't want to wait too long. So let's quickly hop over to the to an already finished result, just to save some time on this. We'll just give it another minute and then we'll visualize it. So that's what we've seen, right? So we will see in a second in the post-processor then that that we need to visualize it here, that the high velocities are here, right? And that we now can actually use this and inform our design process moving forward, right? And this was the initial layout, right? The initial layout that we would that we started with, and based on this information, knowing that these channels, that these open places see at least some sort of acceleration of the wind, we could now inform our design process and say, okay, look, at this stage in the project, it's very simple, very easy to quickly switch over the approach here and bring in some vegetation in this point, right? You can see the little vegetation elements I brought in here, and that would be now straightforward, to rotate them, to change them, maybe to bring in other things I would want to bring in, etc. So you just have the information you need to actually do this, right? Okay, and in the meantime, let's quickly hop over just to see how this looks like. So this is now the result that we have, right? Let's see. So this took now 5 minutes and 4 core hours, right? So almost nothing. This was a super cheap analysis. And this is now how it looks like, right? So let's do a quick post-processing here. We'll hide the fluid volume and this and this. We don't need this. These are different elements we would use in other analysis. Let's make this look a bit nice. Again, this is the master plan we looked at, right? And now what we can do is we'll bring in a cut plane. And we want to have this cut plane at 1.75 meters. This is where most of our customers are analyzing pedestrian wind comfort. And we're not interested in pressure. What we're interested in is primarily velocity, right? Here you see the Cartesian approach, we node average that and tune up the velocity a bit, right? And now we can see immediately, okay, this took now 5 minutes, right, to get a first analysis done. This is a transient result, so we can also animate this. Let's quickly see. Again, initially, of course, some effects that then quickly pan out, and we can see vortices shedding through, right? Because it's a very rough analysis, right? There's not a lot of vortices happening because the resolution is very low. But now, just in a matter of minutes, I could tune up the resolution and get a more fine-grained result, right? This is how the end-to-end process works, right? Just 10 minutes of work. Okay, and then based on these insights, what we would bring in is additional elements, and of course, we would reiterate this process. We'll just duplicate the simulation setup, bring in the new elements, and run this again. So here you can see that it might not have been the smartest choice because we can still see some channel effects here, some Venturi effects, but it seems to be already better, right? And we see a lot of customers then having great ideas and oftentimes you can change the building shape, or on a second look, when I look at this, we might actually want to change the form of the shape of the building here at the top, etc. Right? All of these things can now be just quickly iterated, and more informed design decisions can be made. This really hopefully gave you a feeling for how you can incorporate CFD, and specifically CFD on SimScale, in an early design, in an early phase of the design process, where it's faster, more iterative. Looking at the clock, we're running a bit behind, so I'm going to speed up the rest now slightly, because the second scenario, keep in mind, quick recap, we talked about very quick iterative design studies in the beginning, and then more and not so high accuracy, and then tuning up the accuracy, throwing more cells at the problem, using more cells to get higher fidelity results. This is now, you can see already a master plan that has a lot of detail contained, right? We see some vegetation here on the left. We can see the terrain is modeled within it as well. We can see a lot of detail already on the facades, etc. So this seems to be, or is definitely a CAD model from a later stage of the design process. Also here, same methodology, right? You would certainly tune up the resolution, use more computing power to actually capture all the detail in that model, but the process is very similar. But we'll not go through the entire live demo, right? Because these simulations also go faster. The approach is then slightly different as well, right? We talked about this already earlier, but now in such a detailed study, what we see most customers doing is you start again with local weather information, right? But this time you're going to look at all wind directions. It really depends on which country, but typically we see between 8 to 36 wind directions depending on the project. And so for each of these wind directions, you run a CFD analysis, and then it depends on the specific criteria and the specific code you use, but oftentimes it has some sort of normalizing the velocities you're seeing to some reference velocity, oftentimes the velocity at 60 meters height, or some other reference velocity. And then these different these different velocities inside the map are then being weighed by how often they happen throughout the year, and that gives you then really a map of the local wind comfort throughout the year, right? And this on the right is a visualization of the Lawson criteria, and so we can see on the x-axis the amount of time throughout the year where a specific gust speed has been exceeded. And on the y-axis, we can see the wind speed. Right? In that case, the before scale. And here you can, just a visualization of where you are and where you want to be in your comfort map. At the bottom, a quick list of, we see many different standards, many different codes being used. Right. What we see very often is the Davenport criteria, and also Lawson, but at times also Melbourne. There's in the Netherlands the NE 8100. So there's different codes that are being used, and all of them have their subtle differences and require a different way of computing it. But the input CFD provides is all the time the same. And just a super quick case study, right? We already saw the CAD model. That's a building we're very fascinated with here at SimScale. Yeah, beautiful tower that's being built in New York at the moment. And just, I think it's a great case study, right? It's directly at Central Park, so we have some vegetation around it, we have some terrain around it, and some incoming wind coming from the park onto the building, and then you can assess what it does to the local wind comfort around it. The CAD model, we looked at it quickly before, right? Very, very detailed, a lot of facade detail already on it. There's vegetation, terrain, etc. It's not cleaned, it's just being brought in as is into SimScale. In this case, we spent more time on driving and tuning the resolution depending on where we want high fidelity results, right? Before, you've seen that we just used basically a brute force approach, right? We had one cell size with one resolution across the entire domain. In such an analysis, it would spend more time tuning your setup. Again, we'll not go into details here, but you've seen how I apply the surface refinement to all surfaces, right? And here you would tune the resolution around the tower of interest very high to make sure that your Y plus is good there, that your boundary layer is captured well there, and the further you go away from the area of interest, you would save cells. Yes, that's what we talked about, right? Wind direction coming from the left. We'll just look at one, right? And then a quick analysis. Oh yeah, important piece to note here as well. This is actually a proper atmospheric boundary layer being brought in, right? So the turbulence as a function of height over the terrain is being applied properly. Also the velocity, that we capture the incoming wind as accurate as possible. Talked about this. Yeah, and this is then how it looks like, right? So again, the full 3D flow is being captured in a transient analysis. The lattice Boltzmann, by definition, gives you transient flow fields, transient results, and this is how it looks like, right? And let's quickly hop over. Again, we'll not go through the entire project, but just a quick look. Quick look at this. We've seen this before, right? So you can see here, right, that we use much higher resolution. Let's quickly animate this as well. But again, we've seen that before, right? Incoming wind coming from the left, and a much more higher resolution between the buildings and the area of interest. And let's actually check on the stats for this. So this simulation had just short of 100 million lattice cells, right? So cells that are being used to discretize the domain. And it was being computed, I think, in under 2 hours, as far as I know. And that's not primarily what we're interested in, right? This analysis was not about wind loading. It was about pedestrian wind comfort. So also here, right, we get a transient result that's animated right from SimScale. And you could dig deeper, of course, and look at this one wind direction, but typically that now would be the input to a further combination of these different wind directions to get a comfort map of this area. Important piece, again, lattice Boltzmann is by design transient, but you can capture average fields, either a last time step. In this case, we can see a Schlieren plot of the last time step. You can also get an average, basically an average across multiple time steps, if you want to deal rather with steady state data as well. Again, I don't want to go into too much detail because we're already pretty much towards the end of the session. Pressure is being computed, all turbulent quantities are being computed. At times we see customers being interested in detecting low pressure areas, if there's some gas that is being distributed as well, which we can see here, right? But also here, I don't want to get too much into detail. The important piece to note is here we would spend a significant significantly higher investment into computing this, right? The beauty of this lattice Boltzmann solver, it's that it's parallelized across multiple GPUs, right? So in case of doubt, 8 or 16 GPUs are being used to compute one simulation, and you can compute 36 wind directions in parallel, right? So you have dozens of GPUs running simultaneously for getting your job done, which cuts down your turnaround times, but you do not have to pay or purchase all of this hardware and to have it in your basement, right? And this is one of the reasons why we're seeing so much success in the architecture space, because of its project nature, because it's a one-off need for simulation. SimScale comes in very handy for these types of project settings. All right, let me quickly wrap this up. What we've seen today is two very different uses of CFD in an architectural setting, in an AEC project. The first one we ran in under, I would say, don't cite me on that, but I would say in under 8 minutes, we went from a very complex Rhino building model. Let's quickly bring that up as well. Where did we have it? Over here. We went from a very complex Rhino building model, this one, right, to simulation to get a first velocity distribution for one of the primary wind direction in under 10 minutes, right? Thanks to a lattice Boltzmann solver that deals gracefully with complex geometry, thanks to the that there's no meshing process involved, etc. All of this is integrated into the solver, and it allows you to quickly iterate over different designs in a very short amount of time. The second scenario we've seen is using the exact same solver, the exact same workflow, by just turning up the resolution with which we want to capture the aerodynamic effects inside the city, going to a very accurate but more time-consuming analysis that I would use in a later stage of the design process. All of this put together is basically that the exact same workflow, the exact same product, the exact same technology is being used in two very different projects, which makes it an ideal, a great piece of software that's being used by a lot of AEC firms already. If you're interested in that, we'd love to talk. That being said, this wraps up the official part of the webinar, right? And I went definitely over time. I didn't think that I'd use that much time, but let's quickly see if there's a couple of questions we can answer at that point. Before I do that, even if I see already there's a lot of questions, so I'm pretty sure we won't be able to answer all of them today. If we can't, I'd really encourage you to reach out to us. Go to our website. There's a lot of contacts. There's a forum. There's support at simscale.com. We're really happy to talk about your specific application. Okay, now let's quickly see. One audience member asks whether or not it's possible for the lattice Boltzmann solver that we showed if it already supports rotating machinery, so rotating elements. The quick answer is no, not right now. It's really being built. The types of applications, so let's quickly go back. These types of applications, these external analysis, right, both wind loading as well as pedestrian wind comfort is really the targeted applications that it's being built for right now, that it's being validated, that we see a lot of interest in. That being said, there's both interest from the automotive sector. There's a lot of automotive applications, as well as from energy, what you're referring to, where rotating machinery would be required, right? So this is definitely something we're looking into, and that's being considered. But right now in the production system, there is no rotating zones available in lattice Boltzmann, in the lattice Boltzmann solver. Of course, we have a lot of customers running rotating machinery on SimScale, but they're using the finite element solver, the finite volume solvers on SimScale to get that job done. One audience member asks whether or not a circular computational domain would be used to facilitate different wind directions. And if so, how the boundary conditions would be set up. Good questions. Paid well attention to the workflow. So for the lattice Boltzmann solver workflow we've seen, you wouldn't use a circular computational domain in for the finite volume solvers on SimScale. We see a lot of customers doing exactly that. At times, either a computational domain for with 8 that facilitates 8 different directions, or 36 different directions, or even a circular domain. So we've seen all of this. But for the lattice-Boltzmann solver, it would always be a Cartesian box. That being said, one of the features that are being released this week is an automated way to change the domain angle, right? So what you would do, the workflow would be the exact same way, but you will have a setting for your computational domain where you can simply rotate it, right? That was a request from a lot of customers we had, because all of our customers wanted to keep they didn't want to rotate the city model, because you want to keep your points of interest, your probe points, the probe locations, etc. In post-processing, you want to maintain them, right? You don't want to change them and update them for every rotation. And so it'll be a simple rotating of your box, and then the boundary condition will remain the same. I hope that answers the questions. So I'm already seeing, maybe let's pick one additional question, but there's really too many to answer at that point. Let's see. One audience member asks, what's the maximum size of the model that can be imported, and are there restrictions on the computational domain sizes? Also, very good questions, because so the short answer is no. From a geometrical point of view, you can bring everything in, right? Even, I'm not sure who's familiar with Parasolid, but there's constraints on a modeling box inside Parasolid, but we basically enable also models that are being, bigger than a kilometer. So we're regularly seeing customers bringing in, not like 10 kilometers, but definitely more than a kilometer for a model. That being said, the Reynolds numbers you're getting into, right, depending on the wind speed, etc., are quite significant, right? So there are some options in the simulation setup for Reynolds scaling, and it's documented in how that can be done. But fundamentally, there is no limit on the computational domain that you can define here. If you want to dig into this as well, there's 4 or 5 already at this point published projects of large cities or buildings that are being simulated with this lattice-Boltzmann solver, and compared to reference data from academia. So I definitely recommend, and Reynolds scaling is covered, and I definitely recommend checking this out. It's an interesting read. All right, last question, because I think this is something a lot of customers asked before. Two. This one is also good. One question is it possible that the user-defined, that the atmospheric boundary layer is being defined as a user-defined function? Yes, it is. So in fact, the function, I'm not sure. So most of our customers, what they are doing is they're bringing a CSV file in, right? And so you're essentially saying as a function of your height above the ground, this is the velocity and this is the turbulent intensity that I'm having at this height. And this is something all of our, the moment you're getting into some fidelity with this analysis, this is something what all of them do. Yep, and then also a good question that we're getting a lot as well. One user asks whether or not this solver can be used to calculate aeroacoustics. So let me put it this way: it's not something that we promote or we do a lot of webinars with, but there is users that are using it specifically for this, right? Because there's LES turbulence models and different DDES turbulence models in there. It's already on the way towards supporting such aeroacoustic phenomena as well, right? And so while you don't get the output from a full aeroacoustic lattice-Boltzmann solver yet, the pressure fields and contours that you're computing, that you can compute in all of them, transient and in a very fast turnaround times, makes it already now compelling for such use cases as well. All right. So there's more questions here, but I think some of them are very detailed, and I would follow up on them in a one-on-one with emails. And so I'll wrap up this webinar officially, but not before I said, thanks to everyone that spent this 60 minutes with us. I hope with something that's relevant to your work. And again, stating the obvious, we'd love to talk. If you have some application, some project you could foresee using this technology in, but you're not sure of, give us a ring, shoot us an email. We'd love to get engaged and see whether or not this is a tool that's valuable for your work. So again, thank you so much, and have a great day. Bye-bye.